Today we are going to be finishing up Gauss's law. We're going to kind of quickly go through that. I'm going to have to make some edits. Okay, so as a reminder, you all have the quiz today for electric force and charge, so make certain you get that done, because if you don't, then you don't get points for it, and that's that. The next quiz is this coming Wednesday, and that's going to be on Gauss's law and electric fields. I don't know why this isn't showing, so I'm going to keep fiddling with it while I talk. If it works, it works. If it doesn't, we'll figure it out. But yeah, the next quiz coming up this next Wednesday. I am going to need to make some edits to the problem set, because originally there's a lot of problems. Right, there it is. There's a lot of problems on Gauss's law, which is, again, as I mentioned, you all finding electric fields due to basically spheres, planes, and lines of charge. And Gauss's law is useful, especially if you're a physics major. You're going to see that when you get down the road, but a lot of you are not going to end up needing it too much. So I'm not going to spend as much time emphasizing it this semester as I did last semester. There is some pieces and some concepts I'm going to need you all to know, and I'll clarify what those are as we go through the slides. But I'm not going to go as in-depth as I did last time, so I'm going to change some of the problems in the problem set to address that. All right, so that's that. One thing I posted on the page that also has the, so as I mentioned, screen cap, that's on the Pages tab. If you haven't seen it yet, Pages, when you go here, every single class I upload a screen cap of what's going on with my voice. But if I'm ever doing any extra thing, that'll also be here. So in this case, there's this really nifty simulation that you can mess with on your own. This FALSID website just has a ton of these things. And this is basically just a simulation of what the electric field looks like. So the brighter the lines, the stronger it is, and they get a little dimmer as you get farther away. But the nifty thing is you can do this for like a bunch of things. So he has all sorts of shapes. So here's what it looks like for a square. And as I mentioned, so the inside is 0, because the electric field inside a conductor is 0. And you actually get some stronger ones in the corners, like I mentioned to you before. There's dipoles. So you can see all the different electric fields with all the arrows. So this is just a really nice visualization of what the electric field looks like, due to a bunch of different geometries. So if it's something you want to mess with, please do. You can then change. You can increase equal potential. We'll talk about that eventually. There's various parameters you can usually change with this thing. So I don't know, just something fun to play around with. If you have some free time, it's interesting. And it's a good visualization if electric fields are weird to you and they don't make sense. This is good. All right. So that is that. Reminder of last class, we talked about flux. We said flux is basically this amount of field lines that pass through the surface of something. We characterized it as this equation. We said the electric flux, the symbol here is capital Phi, that's the equation for flux, is the E field dot product with the A, and that is just the magnitude of E, magnitude of A, times cosine of theta. Real quick, I'm going to kind of talk about this because no one talked about it when I learned about stuff and it was confusing. You are going to see dot products and cross products really commonly. Like you're going to see these moving forward all the time. And one thing that was confusing to me is everyone always just said, oh, it's just multiplying vectors. But then why is there two different ways of multiplying vectors? What's up with that? Well, to understand this dot product, to understand why it's this cosine theta, it's actually a really simple explanation. So if I have an area vector that is pointed, for instance, this way, and I have an electric field vector pointed this way. Remember, the angle, this cosine theta, that angle corresponds to the angle between them. When I do this E times A times cosine theta, what that effectively is doing, so in this case it's pretty easy to see the way I've drawn it, is E times cosine of theta gives me the component of E cosine of theta, the component of E that is aligned with A. So when you're doing a dot product, you're basically multiplying the parts of the vector that are parallel to each other. That is what a dot product is doing. When you're doing a sign, or when you get to cross products, you're multiplying the parts of the vectors that are perpendicular to each other. Okay, so dot product, multiplying the parts of the vectors that are parallel, cross product, multiplying the parts that are perpendicular. I don't know, that's something to me that no one, and if that doesn't make sense, please ask me more, because you're going to see this a bunch. and I want the dot product and cross product to make sense to you, because if you're using a tool, you should know how it works. It's just a good rule of thumb. So that's that. Okay. So with that in mind, I'm going to go ahead and start. We did the problem last time. We found the flux through this one, went really quickly. We're going to continue to do another couple practice ones where you are going to test if you remember how to do it. And then we're going to kind of move forward into a couple more flux things and then Gauss's law. Reminder, today I am grading your clicker questions, giving you all 2 weeks now. Plenty of time to get your clicker. So today is officially the day where I'm starting to grade these. This is part of your course grade. You get a credit for getting it right. You get credit for answering it at all, anything. So spend your time, put the effort in, try to get the right answer, but if you don't, that's not a big deal. You still get half the credit for just doing it. So this problem, asking for the electric field through this piece of this flux. I will show you all visually what this looks like in the case that it's not clear. The electric field is going left to right. The electric field is 100 newtons per coulomb, left to right, and the piece of paper, the surface is flat. Left to right, flat. Okay. Whereas in the previous problem, it was not flat. It was up and down. Everything else is the same. And it's a 2x2 piece of whatever. Paper or something. Doesn't really matter. Gonna give you all about 10 more seconds. I'm guessing there's about 200 of you on here, so still missing some people. All right, in 5, 4, 3, 2, 1. All right. Okay, so let's go ahead and do this problem. We're trying to find flux. So what are we trying to find? This thing. This is the problem-solving process. We need to find this. Then we have to remember, what's the equations? What's the concepts for that? It's the amount of field lines passing through it. So we're going to use that flux equation. We remember, oh, flux, this is the equation for it. E times A times cosine of theta, assuming the angle is constant and the electric field is constant. Electric field's constant, the angle's constant. Next thing is we need to remember how to get the area vector. Remember the tip I told you is literally just take whatever it has and put your pencil on it. So in this case, here's my thing. So the area vector is going to point either straight up or straight down. Again, it doesn't really matter. We're going to get the same answer. But the area vector is perpendicular to the surface. That means my electric field, I just moved it over from the left. You can do that. And you see here, angle is 90 degrees. So you get E times A times cosine of 90. Cosine of 90 is 0. So the answer is going to be 0. Remember, the way to think about flux is how many field lines pass through the surface. How many field lines pass through the surface? If it's like this, nothing's passing through it. It's one way of conceptualizing this. If there was some other angle, I would have to multiply 2 by 2 to get 4, and that would give you the magnitude of A. So the magnitude of A here is 4. Magnitude of E is 100 newtons per coulomb. Magnitude of A is 4 meters squared. Okay, great. More practice. Same exact problem, but now our surface is at a 20-degree angle to the XZ plane. XZ plane, imagining this is Z, this is X. Basically, it's 20 degrees from being flat. 20 degrees above being flat. So you can see it here in this picture. So spend some time, think about it. I guess I could just XZ plane this. Apologies, XZ should actually be this way. There you go. Picture's still fine. Alright, get your answer and then check to make certain it makes sense. One of my tips to you with this problem is think of as this angle increases, does my answer get bigger or smaller? As my thing tilts more and more, that's one way to kind of check your answer on this. As this tilts more and more upwards, should the flux be increasing or decreasing? Alright, give you all about 10 more seconds. Alright, in 5, 4, 3, 2, 1. Okay, so to think through this problem, before I even give you all the answer, I'm going to give you a quick question. Is this closer to being flat or is this closer to being standing up? So is it closer to being flat or is it closer to being standing up? Who said this closer to being flat? Everyone. Okay, great. Who said this closer to being standing up? One person, great. Appreciate your aplomb. All right, so if it is closer to being flat, that means when it was flat, was the flux 0 or was the flux maximum? Who says 0? Who says maximum? Great. It is closer to being 0. So that is one way to check your answer to this. Remember, now here's the third step in that. Cosine. Is it the largest when it's 0? Or is it the largest when the angle is 0? Or is it largest when the angle is 90 degrees? 0. So, cosine, largest, theta equals 0, and this object is closer to being flat. Flat, therefore closer to phi equaling 0. Okay? So that's one way to check our answer. Because basically, as this angle decreases, our flux will decrease. As this angle increases, our flux will increase. So, let's figure out what the right angle is now, and we're going to actually do it with some geometry. So this is our area vector. This is our area vector, and this is our electric field. Here's the tricky part. This angle is 20 degrees. This angle is 70 degrees. How did I know that? You're going to have to use some trigonometry or geometry. We can draw the arrows over here instead. And there's our electric field. And so, So there's a couple ways to think about this. One, you can do some geometry. Two, you can recognize my answer. So I'll tell you all, this is the answer. Either of these are correct. Cosine of 70 is the same thing as sine of 20. It is not cosine of 20 because this angle here is not the angle between the area and the electric field. It is 90 minus that. So the conceptual way that I kind of do these problems is I don't usually do the geometry. I know, when you see these problems, you know it's going to be sine or cosine. Like, that's a quick jump. That's one you've seen enough of. And then the thing to think of is cosine of 20 degrees. That is closer to being the maximum value. Cosine of 20 is closer to being the maximum, whereas cosine of 70 is closer to being the minimum. You know it's closer to being flat, so it should be closer to the minimum. So you know that the flux should be closer to the minimum. So your angle, when you do that cosine or whatever, that should give you an answer that's closer to the minimum. Does that make sense? Does that seem weird? Think of it this way. As I decrease this angle, my cosine should be going to 90. As I decrease this thing, it should be going closer to 90. And it can only decrease 20 degrees. So this will increase by 20 and get to 90. If I increase this by 20 degrees, so if it dropped to being flat, that means it is no longer a 20 degree angle, it's flat. I would add 20 degrees to that cosine of 20 and I'd get cosine of 40, which is wrong. So there's a lot of kind of conceptual checks for this, but you have to be really careful. It's really simple to just be like, oh, the angle I gave you is the one I'm going to plug in. No, you have to actually check your geometry, check to make certain the logic makes sense. All right. And I kind of got half and half answers on this one. Oh, I got more than, okay. It was better than it looked like on my little receiver. So make sure that makes sense to you. If not, please come ask me questions after, or just think on it more in your own time, whatever you prefer. Okay, so far we've been doing 2D, so just like it was EA cosine theta. Now our area vector is changing on each surface. So for instance, the square, the area vector here, what you would do is you would do one side at a time. You would do this side, then this side, then this side, then this side. Because on this side, the right side of the square, we show an electric field going in and an area going out. They're both constant, so I can just easily do EA cosine theta, done. This side, constant, constant, constant. So you split it up into pieces you can add. The sphere looks a little complicated. You may be like, oh, that's a curved surface. That's going to make my life hard. The nice thing is, in this problem, the electric field points exactly outward. The area vector on a sphere also always points exactly outward. Remember, do that same thing. I'm just going to, I don't have anything spherical around me. This is the closest thing I've got. Remember, if you have any kind of curved surface, again, just put your pencil on it, the eraser flattened down, and you can see as I move down this curved surface, it tracks with it. It's going to rotate kind of with it, again, always being perpendicular. And same thing with the cylinder, going to track on the outside. On the tops and bottoms, the area will be this way. So, when you have a complex shape and you have to integrate over it, sometimes it's easier to break it into pieces. That's kind of the rule of thumb there, or the helpful tip. You can break any integral into a summation of other integrals. And then you can sometimes reduce those integrals to make your life easier. Okay. So Gaussian surface, basically we just make up this surface to enclose an object and we use that to calculate the electric field. Again, we're going to kind of quickly talk through that. I'm not going to have you all do as much of that, but the concepts are important. Okay, I'm going to kind of jump back to this. We're going to do some more flux problems and then I'm going to come back to this one. Okay. So another definition of flux, it turns out, is literally just the amount of charge enclosed divided by epsilon naught. So we have two definitions of flux now. We have flux equals the integral of the electric field times the area. And then we have this one, and it's just the charge enclosed over epsilon naught. This definition, these definitions are actually experimentally found. They're not necessarily something you can prove, so that's why kind of I'm just telling you, and that's where we're staying. But then what you can do is you can set these things equal to each other, and that's going to be Gauss's law. So we've done the integral of E dot dA. We are now going to practice doing flux equals charge enclosed over epsilon naught. Epsilon naught is that permittivity of free space. I told you all about that forever ago. Well, forever ago was last week. I don't know what you consider forever. Permittivity of free space. The value of that is 8.854 e to the minus 12. You can hopefully have that somewhere else in these slides. Oh, that's an easy thing you can just look up. It's called epsilon naught. Epsilon because that's the Greek letter epsilon, naught because there's a sub-zero. And this is the permittivity of free space, which basically just means it's a value we give in vacuum for how easy or difficult it is to make an electric field. You have permittivities of all sorts of materials. Everyone has a different permittivity, and then that would just be the permittivity of that material. Free space just means permittivity of vacuum. When there's nothing. Free space, nothing, vacuum, same thing. Okay, so in this picture, we have a bunch of charges. We have and we have our Gaussian, we have some object that we drew around it, so we call this a Gaussian surface, and we want to find the flux through this surface. So what we're going to need to do is find the amount of charge enclosed in this surface. And that's the question to you all. How much charge is enclosed in this surface? What is the net charge? And then you just divide that by epsilon naught. All these are divided by epsilon naught. So hopefully it should be pretty simple. I'll tell you, there is 4 positive charges inside and 2 negative charges. What is the net charge inside it? And all of these have the same magnitude. So 4 positive charges, all of them equal to Q. 2 negative charges, each equal to Q. Should hopefully be pretty quick. Net charge divided by epsilon naught. Net charge enclosed. So there is 2 positive charges outside of it, 4 negative charges outside of it. How many charges are enclosed though? Let me make sure I'm using the same notation. Yep. So inside, or I could have put enclosed, both say the same thing. All right, give you all 5 more seconds. Again, this is real quick. So 5, 4, 3, 2, 1. Great. Okay, so let's add them up. What is Qn? Qn equals 4 minus 2. And we'll throw the Q on the outside because we said they all have Q. Equals 2. All right, very easy, but this is a really common problem. So this, reason we're doing this, because this is the second half of Gauss's law. First half we did flux, we got some practice on that. Second part, now we're getting the charge enclosed. All right, let me see the next slides, whether I want to jump back to the other thing. Great. A little bit more complex problem. I have, so a collection of point charges with Q equals plus or minus 1 coulomb. It's surrounded by a Gaussian surface. Again, it's just like, a Gaussian surface is just an imaginary surface we put around it. It's not like a physical thing. It's a tool that we use to do the problem. So it's just like, basically we're just enclosing these and we're saying what's the flux through this imaginary thing that we've enclosed it in. All right, so it's shown as 2D representation. I have 1, 2, I'll count it out. 1, 2, 3, 4, 5 positive, 1, 2, 3, 4, 5 negative charges. What is the flux through this surface? I'll close it out in 5, 4, 3, 2, 1. Okay, so what is the charge enclosed? Same exact problem as the last one, but now we have numbers. So it is positive 5 coulombs minus 5 coulombs. It's 0. Flux is 0. Great. Again, pretty stupid, like super simple. If you didn't get it, that's okay. Make certain you're just understanding what I'm showing you as the answer. It's okay to get these wrong. Again, getting things wrong is normal. You will find I get many things wrong. But just make certain you're learning from this. So, all that to say, the important thing here is that the charge enclosed is 0, even though there is charges enclosed in it. So there's kind of 2 points I want to stress here. The charge enclosed is 0, but that still means there's charges there. That still means there's something there. So that's important. And the other nifty thing here is it did not matter what the distribution is here. That's the other kind of interesting takeaway. The flux did not depend upon where these charges were located. I randomly put these here. I didn't even verbally describe where they were, just they're random. It does not matter where they are. The flux on the right side of the equation is just charge enclosed over epsilon naught. So it's kind of just a nifty mathematical technique that we can use to do some problems. Okay. And there we go. And just a reminder, 8.854, it's missing the 4, but 8.85 times 10 to the minus 12 is epsilon naught. Okay. So I am now going to show you all the one with the point charge to kind of give you the two pieces together. We've done the right side, we've done the left side. We've done the integral of E dot dA, we've done some problems with that, and we've done Q enclosed over epsilon naught. And we're going to kind of use this to do the most simple example of Gauss's law, which is a point charge, which we already kind of know a solution to, but this is going to be useful to help you kind of see what Gauss's law looks like and to prove that Gauss's law is true. So, flux equals the integral of E dot dA, and flux equals Q enclosed over epsilon naught. So if A equals B and A equals C, then B equals C. So this is Gauss's law. Just set them equal to each other. So we are now going to apply this to the case of a point charge. I'm going to make my point charge positive. The purpose of Gauss's law is to find the electric field. So even though we're using flux and Q enclosed and all these kind of things, the main reason you use Gauss's law is to find the electric field due to systems that are more complicated than we can usually just do with point charges. And again, we're going to show what those systems are. I'm using a point charge now just to prove it against the simplest case. And we already know the electric field, so we'll even start. We know what the solution should be. Remember, this is the electric field due to a point charge. We should get that answer. If we do not get that answer, then it's wrong and something's awful and I don't know what I've learned my whole life. All right, so the next step is basically we're going to say we want to find the electric field here, point P. And again, you may be like, well, why don't we just use this thing over here? Well, we're trying to prove that. So that's why we're not immediately jumping to that. To do this problem, what we're going to do is we're going to choose that Gaussian surface that will make our problem the easiest to solve. You can choose any Gaussian surface you want when doing these problems. There's basically rules, though, in that you want to pick specific ones because people just found they're the easiest to use. We'll clarify what those are. But I will tell you that for this problem, the easiest Gaussian surface is going to be a sphere completely enclosing this charge. It has to be a three-dimensional shape. So even though I drew a circle here, it's a sphere. Sphere Gaussian surface. That's going to be important. And the reason I chose it, and I want you all to figure this out, at this point P, if I made a Gaussian surface here, spend a few seconds, what would be the direction of the electric field at this point? What would be the direction of the area vector? Spend some time, draw it on your paper, make certain you can figure out what would be the direction of the electric field due to this charge, what would be the direction of the area vector at this spot. Spend some time, figure it out. Think about it, and then I'll tell you what it is. Yeah?
And your electric field equation, is that an H or K?
It's a K. Yeah, unfortunately my K's often look like H's when I draw really quick. Yeah, it's the same one we've seen before. This is what we're proving. Proving this. So we already know this is the answer. All right. So hopefully you tried it. Because again, this is the only way you're going to learn is trying things. So remember, the electric field always points away from a positive charge. That rule still holds. And let's go ahead and just do that thing where I take my pencil and I plop it on my surface such that it's flat on there. There you go. It is in the same exact direction as E. The area vector at this exact point is the same exact direction as E. I picked an arbitrary point here. This point here is random. I didn't say specifically the top left part of a sphere, the area vector and electric field's like it. That is true of every single spot on this sphere. Every single spot, the area vector and the electric field vector point in the same direction. This is important because this is what this integral is doing, is adding up all of the contributions of every single one of these. So, when it does that, we'll move over here. So we're just going to do one side at a time. E dot dA. It broke again. I have no idea why. Maybe if I wiggle it around. Hey, it worked. All right. We also know that this is symmetrical. Remember, we know, so this is one of those, you just kind of have to remember that the electric field is going to be due to a set distance. So because the sphere, this distance is the same as this distance is the same as any distance away on that sphere. We put the center where the charge is. So we know that the electric field is constant. And I'll even do this first. We know E, we can go ahead and convert it to this because we know the angle is constant. Angle is constant. And the theta equals 0, not 90. 0 because E and A at every single spot are parallel. We know E is constant because everywhere in the sphere is the same distance. So we can pull out E. And then it's just the integral of dA because cosine of theta of 0 equals just 1. So we don't need to worry about that anymore. All right. Again, it's been a few seconds now. What's going to be the integral of dA over a sphere? Just spend some time. See if you can remember. Maybe like 20 seconds. If I integrate dA over a sphere, what do you think it's going to give me? Rack your brain. All right. It will give you the area of a sphere. Woo! What is the area of a sphere? 4/3 pi r cubed. Oh, nope, that's the volume. 4 pi r squared. There you go. 4/3 pi r cubed is the volume. Don't put the volume. Okay, great. We have done one side of the equation. Unfortunately, I'm kind of running out of space here. So, apologies, it's going to be a bit messy. But now I'm going to do Q enclosed. So this is kind of one piece. I'm going to jump to another slide just to give myself more space. So we did integral of E dot dA equals Q enclosed over epsilon naught. We did this side and we got E times 4 pi r squared. Let's do this side. Over here. And what's Q enclosed over epsilon naught? It's just Q over epsilon naught. Well, that was quick. Why is it Q over epsilon naught? Because how much charge is enclosed by this? Q. Again, you all have done this at this point. All right. So, it's Q over epsilon naught. And now when we solve for E, because this is the main application of Gauss's law, it is going to be Q over 4 pi r squared epsilon naught. Remember, we are trying to get kq over r squared. And this is where you just do some 1 over 4 pi epsilon naught. All I'm doing is rearranging terms. And remember that 1 over 4 pi epsilon naught is k. There you go. So that is our quick kind of, this is how you would use Gauss's law. You have some charge, you draw a Gaussian surface around it that makes the math easy. That's basically the math, the one you choose, and the rules are you're going to choose one either that the angle is constant or the angle is, constant such that it equals cosine of, it's either 0 or 90. You either want that angle to give you cosine of 0, which is 1, or cosine 90, which is 0, and then that term would go away. Okay, there you go. And this is a more typed up version of it if you want to see that instead. They're both there. Same thing though. All right. So we've done a Gauss's law. I'm not going to do that one because it's more the same. This is Gauss's law. Just told you all that. Just did it for point charge. Okay. I will give you all some more information for this before we even do this. In fact, give you some information. So this problem shows a cube with a bunch of electric fields either going into sides of it or going out of sides of it. So for instance, on this side, it's going in. On the opposite side, it's going out. This side it's going out, this side it's going in, this side it's going out, this side it's going in. And the problem is asking you, what would be the enclosed charge? It's kind of a black box. We can't see on the inside. So we need to figure out what the enclosed charge is based on this. I'll tell you that these electric fields are constant along every part of this side. So it's 15 at every, 15 here, 15 here, 15 here. And I'll tell you all the area vectors are going to point outward on every side. Area vector, area vector, area vector. And I'll even do one more step for you. What's the angle between these two vectors here? If this one's pointed out and the other one's pointed in, what's that going to give you? 180. So in this case, theta equals 180. What is cosine of 180? -1. That negative matters. All right, giving you a lot of things here then. Figure out whether the enclosed charge is positive, negative, 0. I'll tell you, you can do this conceptually. You can just think about the problem, or you could use Gauss's law and just kind of set up the problem. Remember, adding up each side as an individual side. And just kind of stretch your brain a little bit. Yep.
You said those like 10 20s, you said all those.
No. They're the number they're supposed to be. So the bottom is 20 going in. What I was telling you is that this arrow here, 20, it is 20 going into the bottom at every single spot on the bottom.
Oh, okay.
So it's a constant field on each side, either going into it or going out of it, and the number is given. So it's 10 coming out on the left, 15 going out on the right, 20 going out on the back, 15 going in on the front, 15 going in on the top, 20 going in on the bottom. What is the net enclosed charge? All right, gonna give you all like 5 more seconds. All right, in 5, 4, 3, 2, 1. All right, so I'm gonna go ahead and do the 2 different ways of solving it. I'm gonna do the long way the brute force method, which is basically the mathematical way, and then I'll do the conceptual way second. So, told you all you want to use Gauss's law, so let's set that up. That's going to be the longer way. And when we set this up, we're going to see how this is useful. We want to figure out if the net charge enclosed is positive or negative. So therefore, if we figure out if this left side is positive, then Q is going to be positive. If the left side is negative, then Q is going to be negative. Remember when I said that when we have these multiple sides, you can split this integral into multiple things. So I'm going to split this integral into 6 additions, adding each individual side. And I can give you the side, so we're going to make up that the side of this thing is D. That's fine. Okay, so let's just consider this outward side. We'll call this one, I can't really label the sides because it's kind of a nightmare. But hopefully it'll make sense as I'm going through it, which side is which. So we have 15 going in, 15 going in, and then the side is D squared. And we just said that this angle is 180, so it's cosine of 180. That's that first side here, the outward side. One side done. Left side, plus 10 D squared. Area vector here is going to point this way, so it's cosine of 0. Plus right side, 15 D squared, cosine of 0. Bottom side, 20 times D squared times cosine of 180, because the area vector is that way. Top side, 15 D squared, cosine of 180, and I think we're just missing the back side. Again, area vectors like that. Plus 20 D squared, cosine of 0. All right, so I have 1, 2, 3, 4, 5, 6. Great, I have 6 terms. If you got less than 6 terms, you did it wrong. If you got more than 6 terms, you did it wrong. You have too many sides of a square. All right, so this term's negative, positive, positive, negative, negative, positive. So I'm just unfortunately gonna have to kind of bump it up here. I'm gonna pull out that D squared because who cares, it's a positive number. I don't know what number exactly that gives you. I know it's negative though. Check it on your calculator. Negative 15 plus 10 plus 15 minus 20 minus 15 plus 20 negative 5. There you go. And there's a D squared there, but D squared is going to, so it's negative. So we did all that work, so that's the mathematical way. So it's negative, this equals Q over epsilon naught. Epsilon naught is positive, therefore Q has to be negative. Done. The quick way you could have done this is you conceptually remember to electric field lines for negative charges. Do they point in or out? Who says outward? Do electric fields point outward for negative charge? No. Do they point inward for negative charge? Yes. So basically you just need to figure out, do I have more pointing in than out? And you do. Because all the ones pointing in gave you that negative. Okay. Fantastic. All right, there's 2 more things I want to try to get through today. I may not be able to get through both, but we're going to try. All right, not going to worry about that. Okay. Need everyone's attention for this last little bit so we can try to get through them. There's 2 more concepts I want to try to get to you all. One of them is there are 3 geometries we use Gauss's law for. A line of charge. This line of charge can have a thickness. In our case, this one it doesn't, but it could have a thickness, so it's like a cylinder of charge, a plane of charge, and a sphere of charge. Those are basically the 3 bodies that we use Gauss's law for. And then we choose different Gaussian surfaces for each one. And I'll talk about that, I'll probably have to talk about that more next time. But I want to talk about here is this thing called charge density. Charge density is kind of like regular mass density. Mass density is how much mass do I have per volume. That's what you all have seen at this point. Hopefully you're familiar with that concept. Charge density is going to be how much charge you have, and it depends. So in this case, if it's a linear, this is a 1D situation. 1D meaning one-dimensional. So it is how much charge per meter. We use lambda for that. Lambda is just a Greek letter for it. And the way you would find lambda is you would take the net charge. This is assuming it's uniformly distributed. If it's not, you have to do an integral over the distance. So say this is my rod and it has a distance d and it has a net charge negative q. You would do q over d and that would tell you how much charge I have per meter. So if this thing had a charge of 3 and the distance was 2, I'd have 1.5 coulombs per meter. That meant if I had 5 meters of the thing, I would just multiply that and that would give me how much it has. This exact concept then just kind of translates to the next one. This is 2D. It's a two-dimensional flat surface. This is nu. That's the Greek letter nu. It's kind of funky sounding. Sometimes they use sigma. They mean the exact same thing. I traditionally more so use sigma. You'll see this more often for any kind of surface density. But they're interchangeable. This tells you the charge per meter squared. So how are we going to do that one? Well, we're going to do the charge divided by the area. How much charge is there per meter squared? Okay. Last one is our three-dimensional object. It's a sphere. This is rho, which is what you've actually seen for density before in like your chemistry class for mass. But now we're using it for charge. So rho, which is this kind of slightly slanted P-looking thing, is charge over volume. Okay? So those are our three situations here. I am going to give you problems. This is one of the things I am going to ask you to do, and this is because it's a skill that I think should be important for you to know. For instance, I will say, here's my sphere. Imagine I drew a Gaussian surface. Again, that's just an imaginary surface. So say this thing has a radius of big R, and this has a little radius of little r. I want to find how much charge is enclosed in the little radius. Those are some of the problems I'm going to have you doing. To do that, you will find the charge density of the whole thing. You'll find how the charge is distributed, and then you'll just multiply that by the volume of the inside one. We're going to do some practice problems with that. I'm not going to have you all do that until I give you some practice. What that means is I'm probably going to postpone the second quiz until next Friday. Check if it makes sense. We just have a few more slides, and it looks like a lot, but I'm going to skip through a lot of these. Have a wonderful weekend. I'm postponing quiz 2, not quiz 1. Quiz 1 is still due today.